Okay, guys, we got the easy stuff out of the way. Now it gets a little bit tougher. We're going to be calculating equilibrium concentrations again, but this time not from an initial condition where we're at equilibrium. We're going to start off with initial conditions that are not at equilibrium, and we're being asked to calculate the equilibrium concentrations for all three of the species in this particular reaction. So the first thing I want to do is still write an equilibrium expression. K is equal to the concentration of my product squared over the concentrations of my two reactants. I do need to make sure that they are all either gas or aqueous. They are. And I need to make sure that I use coefficients as exponents, and I have. But that's where this problem kind of diverges from the problems that we've done so far. Since we're not at equilibrium, I can't just plug into that equation and just solve. So instead, I need to set up what's known as an ice table. This is going to be a big part of the rest of our year together, so pay attention closely. An ice table sets out what we call initial conditions. Those are usually given. And so if you look right here, that little zero specifies that those are time zero or initial conditions. And they tell us here we have zero point 0.2 molar H2 and zero point 0.2 molar I2. Because it's not specified, we're going to assume that our initial conditions are such that we don't have any HI. Then we're going to do a change in conditions. Now, I should say that technically this reaction goes in both directions, right? It's a reversible reaction. But at the beginning, which way is it going to go? It's going to go forward. Why? Because we don't have any HI to go in the reverse direction, at least initially. So the change in conditions, I don't know exactly what the change is going to look like, but I know I'm going to lose some of both of my reactants. The negative sign disappeared, draw it back again. Now, y, x, and x? Well, these are both in a 1-to-1 ratio, right? So I know if I lose X amount of H2, I'm going to lose also X amount of I2. Consequently, on the right side, I've got to be careful. I'm going to say that I'm going to gain 2X of HI. That's not because I lost two X's on the left side. It's because it's in a ratio of 2-to-1 to those reactants. So that's where that 2 comes from. At equilibrium, that means I have 0.2 minus X and 0.2 minus X. And over here, I have 2X. Okay, I'm just summing my I and C columns together to give me my equilibrium. So if I plug this into an equilibrium expression, it's going to look like this. It's going to look like 2x all squared. Notice that we use that 2 right here, the coefficient. We use it twice. We use it as part of our stoichiometry, which is what we're doing there. But we also use it again here for our coefficient or for our power. We're dividing by 0.2 minus x times 0.2 minus x. I'm going to actually rewrite that. I'm going to rewrite it this way. They give me the K value at 64 is equal to 2x all squared over 0.2 minus x squared. See what I did there? Now, This is actually a really tough problem to solve, except that we lucked out big time. It's, I think, what your math teacher would call a perfect square. What that means is I can take the square root of both sides of this equation, and I end up with something pretty simple to solve. So if I take the square root of 64, I get 8 equals 2x over 0.2 minus x. So I'm going to cross multiply and say 8 times 0.2, which is 1.6, minus 8x equals 2x. Then I'm going to bring 8x to the other side. I get 1.6 equals 10x. Then I'm going to divide by 10. I get x is equal to 0.160. Now, that x value is not the answer to the question. The question was, what are the equilibrium concentrations? Well, I have to plug that x value back into my equilibrium conditions. So for H2 and I2, it's going to be equal to 0.2 minus x, which is 0.16. What does that come out to? That's 0.04 molar. That's our answer for our two reactants. Now, let's take a look at our product. Our product at equilibrium is just 2x. It's not 2x squared. The concentration is 2x. So HI is equal to 2 times 0.16, which is equal to 0.320 molar. And that is our answer. This is a point. So those should be our answers. Here's a good practice, though. Go back and check to make sure it makes sense. If I plug in my equilibrium concentrations into this initial expression, I should get 64. So if I say 0.32 squared divided by 0.04 times 0.04, that should be equal to 64. Let's check it out. 0.32 squared divided by 0.04 divided by 0.04, and it comes out to 64. So that is a correct answer. It is the correct answer. All right. Because we had a perfect square there, life was good, pretty easy. They do get more difficult. We're going to wait till next week to see that. Come back to Google Meet and we'll talk about our homework problem that we're going to do. See you in a minute.